Good morning, everyone. My name is Kulinska, and on behalf of the Atlas Level 1 Central Trigger Group, I will present you another tool for automatic code generation. This time, this one is called HardwareCompiler, that we developed in our group for managing registers and memories in our designs. Yay. Okay. So the talk will start with HardwareCompiler tool description, what it is and why we developed it. And later on, I will present a few examples of its usage in firmware and software development. And at the end, there will be a time for some questions. So, I don't think that I have to explain why we are using code generators to those of you who actually experienced changing the registers in your FPGA designs without their help. So for those of you who managed to not have to do that, let's just say this is not as easy as it looks like. So every change starts from your description, register description, then has to be also implemented in your firmware, and also propagates to software and changes that you need to do there. And this is like every single very small change in the register map that you have to do that generates a lot of tedious work, sometimes for multiple people, not only firmware developers, but also software developers there, and it's very error prone. In our team, we work on Atlas Level 1 Central Trigger System, which is a part of the system that reduces the amount of data gathered by Atlas detector. That was mentioned before, also in previous presentations. And we have a lot of experience in designing multiple boards. Few of them you can see on the slide. So they are using various families of Xilinx FPGAs, from 7 series to Virtrex UltraSky Plus. But there is one thing that all of our designs have in common. So we have to manage hundreds of registers and dozens of memories in them. So that's why in around 2013, an idea of HardwareCompiler tool was born. And it is VHDL and C++ source code generator that generates the code based on one single register map that contains definitions for registers and memories that are used in the design. The tool was originally created only as a software generator, but after we could experience how nice the idea is, then it was also extended to VHDL code generation. And the tool is under constant improvement. Recently, we added very interesting functionality, which is address decoders code generation. So now that we know what HardwareCompiler is, let's see how it fits into our firmware and software development flow. So it all starts with one single register map that is in XML format, and it contains a description of registers and memories that we use in our design. Based on it, HardwareCompiler generates two things. First is VHDL code that then is being included by the designers in our firmware. And second is C++ code that includes simple read and write functions to all the registers and memories that we had in our XML. And this one is then a base for further software development that is also C++ written, as well as thanks to the usage of Python wrapper, we are able to use these methods from C++ in our Python-based test scripts. So what here is very worth pointing out is that this scheme keeps everything consistent. So we have one source file. Based on it, there is automatically generated code and then developers' written code. And this all has one single source of truth. That's why we can keep our firmware development and software development in sync. Also, HardwareCompiler is integrated in our software continuous integration framework, as well as then software build runs on Xilinx MP system on chips, because this is technology that all of our currently developed boards use. So now that we know what how it fits in our process. Let's see where it all starts. So with XML register map. Here you can see an example that is taken from one of our designs of registers and memories defined for muon sector processor FPGA. So at the top, we have a module name with the name of FPGA that these registers and memories here will be used for. And later, below, we have declarations of registers and memories. The declarations are gathered in blocks. Every block is responsible for one firmware functionality. And blocks have their name, address, and additionally a decoder attribute, which will be explained later. So when we look at the first block, it's called TTC block, because it is responsible for managing TTC signals. And here we can see 3 registers. Every register also has a name, an address, and a modifier. Modifier defines whether the register is read-only or read and write. When we look at the second register, it's called countersync, and it also has additional attribute, mask, that trims the register width from default 32 bits into, in this case, 12 bits. When we look at the third register called control, we have something new here, a field. So a field defines certain range of bits that are coming from the register. So field also has a name, in this case reset counter, and the mask that determines which bit of this from available 32 bits from register is used for that field. In this case, it is first bit. And following, we have multiple attribute that converts this one single field into an array of fields, in this case, an array of 2 elements, and offset, the next attribute, informs where the next clone of this field is, in this case, on the 4th bit. So the multiple attribute can also be used with blocks, registers, and memories. It is just creating an array of elements. So now when we look at the second block, we can see at the bottom our first memory declaration. It has a name, sector memory, and first address defined of the memory and its size. Above we can see a play control register that determines how this memory is used. And in this case, it can be used as spy memory or playback memory. Below we can see field called mode, and it has also something new, so we can define numerical values for our fields and then map them into names. So we have, for example, numerical value 2 that is mapped to a name pattern generator, PG. Okay, so now that we are more familiar with structure of our XML, let's see what code is being generated based on it. So HardwareCompiler generates VHDL package that contains declarations for constants, data types, register fields records, as well as conversion functions. So these declarations are generated based on how registers and memories were described in our XML register map. To understand it better, let's look at the example that we have on the right. And the example shows code written by a VHDL developer here that actually includes automatically generated package. At the top, we have package included of this example. So here we have sector logic snap play functionality. And as you can see, control inputs can be directly connected to the fields of spy play control register here. And the naming scheme follows the one from XML, exactly how we defined this register. It is possible thanks to the existence of a control of record for this register inside the package, automatically generated one. Below we can see a memory interface that allows to perform read and writes into the memory that is inside of this functionality. And above we can see also one constant declaration. It is SLI sector memory address width that was generated by HardwareCompiler based on sector memory size attribute from our XML. So what is here very worth mentioning is that our package hide some level of complexity of our XML file from our firmware code, from our VHDL code. So for example, we can change masks of our fields, we can mix them, replace them where they were, and our implementation will stay the same. Only thing that we would have to update is the package here. So let's look at another code that is being generated by HardwareCompiler, and these are registers and memories translator. How the translator is connected to our design, you can see at the diagram above. So we have a translator that is an interface between AXI full bus, single one, and our user logic. So translator drives control signals that are being used in user logic, then can read back status registers, can also perform writes to memory inside the user logic, and read back data from it. So translator is being generated based on decoder block attribute that was mentioned in XML example, and multiple blocks can be included in one decoder, as well as there can be multiple decoders declarations in our XML. We need multiple decoders because our designs use different clock domains, as well as they have different superlogic regions. So the translator is based on Xilinx AXI BRAM controller, IP core, and you can see it, what is inside the translator in this gray box diagram there. And yeah, this IP core interfaces between AXI full and also data signals that are driving BRAMs. So this one performs writes to control registers and drives them. Indirectly can also write to memories and can read from status registers, memories, and also values of control registers back. So here we can see an example of how the translator is connected to the rest of the design. So on the right, we can see a code of automatically generated translator, or what is inside of this instance is an automatically generated code. And on the right, we can see an XML based on which this decoder was generated. So in XML, we have SLI block that is included into the decoder, the right top, that is called SLR1. And this block has two control registers that then are an output from the decoder, like single record that outputs all the control registers from our decoder. The same situation happens with the status registers, read-only registers that are being an input to the decoder, one single record that gathers them all. And also because we have a memory declaration here, we have also an interface here to external memory. So let's leave VHDL and move into software. So HardwareCompiler also generates C++ class that has methods to perform read and write operations for all registers and memories from our XML. And additionally, it generates text-based user interface program that you can see an example of in green box. So the program includes all the top blocks from our XML and also keeps the same naming scheme. And we can enter submenu, in this case, the fourth one, SLI submenu, and see all the read and write methods that were defined for every register and memory in that block. And what is also here worth mentioning is that this is an interactive program. So whatever reads and writes you are doing in this program are actually happening when firmware is running on your design. On the left, we can see an example of a user-written C++ code. We call them high-level software. So they actually use automatically generated C++ methods. Here you can see a read from a spy play control register, changing the field's values, and then writing back to the register. Still, naming scheme in both examples here follows the one from XML. We also like to use Python in our test scripts. And because Python allows us to do iterative development process, so it is very easy for us to change something in XML, then adjust our firmware, and then also software and our Python test scripts are being automatically adjusted to the change that we made. That's why we can do multiple changes and quickly check different versions. So we can use Python thanks to the Swig tool that generates Python wrappers based on C++ header files and a simple user-created interface file. And for us, these are automatically generated C++ classes as well as user-written C++ code. On the right, you can see an example. Also, we have a read from spy play control register, changing fields values, writing back to the register, and again, naming scheme is the same as the one in XML. So to summarize, HardwareCompiler generates VHDL code and C++ code from one single source file. And thanks to, for that, it maintains consistency between firmware and software development, actually for the developers themselves. And it speeds up the development process greatly, hides some level of complexity from our firmware implementation, as well automatically adjusts the software to our tests. So HardwareCompiler is being used for many years in our team, and we are very happy with its performance. So if you are interested in any further information, reach to us. And thank you very much for your attention, and do you have any questions? Thank you very much.
It's all right. Please.
Hello, very nice presentation. We have something similar at our company. A couple of questions. You had a mode register which had a mask and 4 different values. For one, would there be any error checking if your mask was not wide enough for the amount of values you have? Or alternatively, could you consider auto-generating that completely?
So there is this moment when it connects with your code, let's say, because the mask then also in the package, there is a width that is being generated. And yes, there is a moment when this width connects to what you've written before. And yes, if they don't match, then you have an error in your synthesis. So
okay, as long as there's an error that doesn't happen silently, then that's good.
Don't worry, you are always getting an errors there.
And then the second question would be, you had a form called number. Is that an integer, or is that signed or unsigned, or?
I think it's integer, unsigned. Yes.
Yeah. So do you have a signed version as well?
No.
Again, it's a potential for an error if someone misunderstood what it meant.
I don't think so that we have signed.
Okay. Thank you.
Thank you for the presentation. It was very nice. My question is, so I understand you have a single source of truth, which is your XML description. Then you generate VHDL, and that goes one way, and the C++ goes another way. So is there any consistency check when you actually run the system?
This has to be taken care of by developer. So,
Hi, so thank you again for the great project and presentation. So what I understood was that the hardware blocks that you have generated via your VHDL code, you also have C++ functions to read and write to them, right?
To the registers and memories, yes.
Yes, to write to them. Apart from that, if let's say I have a software logic, where number of these blocks have to work in a sequence, in a particular sequence or state machine or something. Is that kind of support possible?
So how we do it is that we have, these methods, and then they write into our registers and memories through the register translators that I also then described. And then what you do afterwards with it, it's up to you. like where you connect this control and status registers, it's fully up for the developer to use later on. What you get from here is a structure of your control and registers that then you can connect to your logic. And here,
Great.
how you use it.
Great. Is this open source or is there a link?
Yes, actually, before the presentation we checked, and it was in a bit closed GitLab repository, but if there is an interest from your side, we'll also make sure that it is open to more people.
Okay, so we need to email you to...
Yes, exactly. Just email us, and yes, we'll make sure that this happens.
Thank you.
Hi, and nice talk. So, going back to the sort of fault tolerance and the consistency between the software and the HDL. So, I've come across problems with this in the past with similar tools, and I'll give you an example. So, I've made my firmware and I've added some new monitoring registers. They're not super important, but I like them, right? And you have one source of truth, right? So now I can have that in my software. So I go and this is physics, so we've got like a big software stack. So I've gone to a lot of trouble to update the software stack. It's taken a week, and now it's updated, and the two are in sync. And now I've found a bug in my firmware, and I have to roll it back. I found a bug in my firmware, so now I have to roll it back. Does the software break?
So when you are using the firmware, okay, so you say that you are changing back the registers afterwards.
Yeah, I think everything should work except my new register. I think the software should not fail, except maybe give a dead value or something like that for that one register that's new. But I don't. This is the problem I've seen. I've seen that the software crashes in other products, right? Not yours.
Yes. So here, if you read from the register that doesn't exist, you will get zeros.
Okay. And a warning, presumably.
I think so.
Okay, that's good. Not keeling over and dying. It's good. Thank you.
I'm sorry.
Thanks for the nice work and nice presentation. And I have the impression that this tool is quite similar to what was developed in Chevy by Tristan. So did you already knew about this tool, or did you thought about maybe joining forces to improve together this register map generator?
So yes, recently we've been learning that there are other tools existing. It would be nice to somehow bring them all together and actually share what other groups are using. But yes, as you can see, this tool, the development started in 2013, so already quite a while ago. And since, we used it for so long, and it is very easy for us to adjust it to what we need, for now we keep with that. So, yeah.
I'm working in the European synchrotron, and we are looking also for a tool to do this register map. So if we manage to find something, to work together in a project, we could also collaborate. So I think it would be nice that we...
If you are interested, reach out to us.
Yes. Thank you.
No problem.
Yeah. Maybe just a comment. Thank you for the presentation. It's related to the same question, actually, because I'm using Chebby, and I think this was not mentioned. There is a companion tool which is called Rexio as well, which is a graphical user tool which actually does exactly the same as you, generate the driver, phasor class, or framework for our software. And there has been a lot of work, and the whole, let's say, accelerator complex now is moving to that. So yeah, indeed, I mean, there is a big effort there to actually merge it to a single tool. I think this is really key message here that we should do.
But Anna, is there support? How many people do you have supporting the tool?
Ralph.
Full time.
So yes, we are a group of firmware developers with Ralph as our support for a tool. Actually, creator of the tool.
No, actually, yes, we need at least to talk to see if we could.
Yes, and yeah, don't forget about Rexio, which is actually also doing the software part. I think this is missing here.
Hi, nice presentation. Just got a quick question, a bit of a daft question, but is this tool compatible with different operating systems? Because one thing I've noticed over the years is a lot of tools are developed for Linux systems, and I can just about get them working on a Windows machine. But sometimes there's some interesting features which I then have to spend time to compensate for. I was just wondering, is this tool compatible with both Windows and Linux, or is it really intended just for one particular operating system?
Yes, it is used on one because we run it on system on chip, and which operating system is there? For us, it's ARMA 9, so it is adjusted to this operating system. I don't think that there have been any trials of using it on Windows. We did not need that, at all.
Okay, thanks. Well, we have yet another tool like this for Felix and for Wupper, the open source PCI Express core. It also generates a document in LaTeX for the registers, which I find very useful. But one question is to you: do you also leave gaps to place new registers for future? If you have a certain block, you leave gaps in your address space, because that's something I find very useful that we do. If you have like an offset somewhere and you want to insert a register, you don't want all the other addresses that come after it to shift.
So this has to be done still by developer, like to ensure that all the addresses fit in your XML register map there. Usually we try to say it is structured in blocks, as I said, and we want a block to be in certain addresses range, so we can connect it to AXI interface. So we just make sure that the address range is big enough for us to fit everything that will be needed for this functionality.
Okay, so if you change something in one block, the addresses of the next one don't change?
Exactly.
Okay, good.
Yes.
Thank you.
But if you are using the same address twice, even if in your multiples of registers, then the hardware compiler will give you an error and inform you about that you are using an address twice.
Thank you so much, Anna, for a clear presentation. Thanks a lot.